So welcome to lecture 24, part 4 for Math 2R03. We've now introduced characteristic polynomials and we've introduced minimal polynomials. In this last part here, I just want to talk about some properties of these two polynomials and how they're related to each other. Now, I'm not going to get into the proofs too much because they kind of use a little bit more kind of abstract algebra techniques. You can go look in the textbook for their proofs, but it's more important that you just remember the statement of the theorem and how to use them. So let's say that you take a linear operator and you have that Q is any polynomial such that when you evaluate it at t, you get 0. Okay, so it's not, this doesn't mean the characteristic polynomial, it just means any polynomial. Then what this theorem says is that the minimal polynomial actually divides that polynomial. Okay, so what that means is you can write Q as the minimal polynomial times some sort of other polynomial for some polynomial Rz. Okay, so one thing that we get is that if you take Qz, it's the characteristic equation. I'm sorry, I shouldn't say characteristic equation. It's the characteristic polynomial. It's the characteristic polynomial of our operator. Then we know that the minimal polynomial Pz of t divides the characteristic polynomial. So you have the characteristic polynomial and the minimal polynomial kind of has to divide that polynomial. Now this is good because we know a little bit about the structure about this polynomial. And in fact, you can prove something a little bit stronger. If you know the minimal polynomial, then you have a root of that polynomial if and only if lambda is one of the eigenvalues. So all the eigenvalues are roots of the minimal polynomial. So putting the pieces together, what we have is lambda 1 through lambda n are the distinct eigenvalues, and let's say you know the multiplicities of each of them. Then we know that the minimal polynomial has to factor into the form of z minus lambda 1, a1, z minus lambda 2, a2, up to z minus lambda m, am, with each of the ai's greater than or equal to 1 and less than or equal to di. And why is this true? Well, first of all, each of the ai's have to be greater than or equal to 1 because we need each of the lambda i's to be roots. If one of the lambda or the ai's was 0, that would mean that term doesn't show up, which would mean that corresponding eigenvalue is not a root. So that's why all the ai's are greater than 1. And then the di, they have to be less than or equal to di because this polynomial has to divide the characteristic polynomial. Okay, so that forces each of these exponents can't be too big. Okay, so the thing that you want to pay attention to is you get some information about what the factorization of the minimal polynomial looks like, but you don't know the ai's exactly. You have to kind of do a little bit of work to get at the ai's. So let me show you kind of an example of this and how you would figure out what the minimal polynomial is. So here, and I'll do it in terms of matrices. So here's our matrix. And just by the fact that it's upper triangular, we can figure out what the eigenvalues are, 1 and 2. And we know that the eigenvalue of 1 has multiplicity 1, and lambda 2 has multiplicity of 3. So that means that the characteristic equation, but polynomial, has the form z minus 1 raised to the power of 1 and z minus 2 raised to the power of 3. So that tells us that the minimal polynomial has to be one of the following. Either has to be z minus 1 times z minus 2, or z minus 1 times z minus 2 squared, or z minus 1, z minus 2 cubed. Okay, and that comes from the fact right over here that the AI has to be between the 1 and the multiplicity. Now, because 1 has multiplicity 1, the only exponent that we can have with z minus 1 is 1, but the exponent for z minus 2 could be 1, 2, or 3. And just to figure out which one is the right one, you just have to see which of these polynomials has the property that when you plug in t, you get the 0 operator. Okay, so our operator in this case is the matrix. We're doing everything in terms of the matrix. So you're looking at the matrix A minus the identity matrix of size 4. And then you have A minus the identity matrix times 2 times size 4. And if you do the calculations, this gives you 0, 0, 0, 0, 1, 0. Okay, so that's what happens when you subtract 1 from everything down the diagonal. And then we have the matrix where we subtract 2 down the diagonal. And we get this matrix right here. And when you multiply them, right, you get 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, and 0, 0, 0, 0. Okay, so this tells me that not the minimal polynomial. Because if it was the minimal polynomial, when we plugged it in, we should get 0. Okay, so, okay, that didn't work. So we have to try the next guy. So we have to look at this particular matrix. And you could do all the work, right? So it's the same matrices as above. Okay, so I'm just quickly writing these things out. And there we go, there's our matrix. But here we have to square it. And if you were to do all the calculations, you would get the 0 matrix at the end. Okay, so this means that this is, so z minus 1, z minus 2 squared is the minimal polynomial. Okay, so if you hadn't figured out, if this one had not been 0, then this one would have to be by default the minimal polynomial. So what we're seeing here is that there's actually a difference between the minimal polynomial and the characteristic polynomial. Okay, so there's kind of like 3 main things for today's lecture. There's the characteristic polynomial, which you would have seen, but we're defining it kind of in a different approach. We first have defined eigenvalues and multiplicities, and then we use that information to define the characteristic polynomial. We then talked about the minimal polynomial, and then we talked about the Cayley-Hamilton theorem, which is kind of a very nice result, which kind of tells us that for any operator over a vector space, when you plug in the operator, there's a polynomial which vanishes at it. And that polynomial, one polynomial that works is the characteristic polynomial. Okay, so that's it for section 8.c. When we come back in the next lecture, we're going to start our discussion of the Jordan form, section 8d. Okay, have a great day.